Hello students, welcome back. Section 4 is the real starting point of chapter 7. Section 4 of this module is the real starting point of chapter 7 of our textbook, the interval estimation, at least the main body of chapter 7. What about sections 1 to 3? They form the theoretical foundation. And of course, this is a 3000 level course, so we have to do the theoretical foundation first, and on top of the foundation, we are building the skill sets. Nonetheless, as far as the exam preparations and your grades are concerned, these problems are more important because they are more standard. You may encounter some A-level problem from sections 1 to 3, but the standard problems are actually coming from now on. Okay, here we go. Here's a brief reminder on point estimate versus interval estimate. Point estimates are the statistics for the parameter. That's basically it, because parameters exist, but nobody knows what they are. So we use sample statistics to make appropriate estimation, and that's a point estimation. Now, after making the point estimation, nothing is accurate in statistics, so always there's going to be error, so plus or minus some error, and you're going to get an interval. And that's what interval estimation is all about. Around X bar, plus or minus something, and you get an interval. Now, this kind of intervals are called confidence intervals, and if it is a 95% confidence interval, is saying there's 95% of chance the real population mean fall in that interval estimation. And of course, the other 5% of the time is going to fail. Similar thing for sample standard deviation versus the population standard deviation. Sample standard deviation and plus minus something, and you get an interval. And if it is, say, 98% confidence interval, then there's 98% of chance that real sigma falls in this interval, and the other 2% of the time it will fail. Okay, so much for confidence interval. And here's a visualization. You see? Here's a visualization of 95% confidence interval we just talked about. We get the point estimate, which is the sample mean, and then plus or minus something, the margin of error, and that'll give me an interval estimate, which is highlighted in blue, and there's 91% of chance that the real population mean will fall here. The other 5% of chance, I'm going to fail, so 2.5% here and 2.5% there. Maybe too low, maybe too high because of the symmetry. Now, if I adjust the confidence level here to 90%, so I'm going to get only 90% of chance that mu will fall into this blue region, so blue region will shrink. You see, it shrunk. There's only 90% of chance that mu will fall here in this interval, so it got smaller. And then this is point estimate, and then margin of error, the biggest possible margin to the end, that got a little bit smaller as well. 90% here, so the other 10% I must fail, so 5% here, 5% there. There goes 90% confidence interval. Let's change it into 99% confidence interval. If I do that, then 99% chance in the middle, and the other 1% I'm going to fail, so 0.5% here, 0.5% there. You see, the middle part, blue part, got bigger. That kind of things are called confidence intervals. Let's go back to the default. Here, another important concept is margin of error, and that is the distance between the point estimate and the endpoint of the interval. The biggest possible error, and that is, let's see, x bar plus something turns out to be z times z times SE. And what is SE? We discussed it. Standard deviation over sigma, the standard deviation sigma over square root of n. And Z, well, we'll discuss it. We'll talk about it in a moment. Here are some example problems of confidence intervals. A certain college selected a random sample of 100 commuting students and obtained the students' one-way commute distance. The resulting sample mean was 10.22 miles. Estimate the mean one-way commute distance of all commuting students of the college using the standard deviation of sigma equals to 6.0 miles. This is a bit strange because we don't know the population mean, so we want to do the estimation, but somehow we do know the population standard deviation, and this is rather weird, ridiculous rather, but let's accept it as is. Let's consider this as a stepping stone toward a little bit more realistic problem where we have to use sample standard deviation here, which will add more uncertainty, and consequently we'll have to consider a little bit different probability distribution. In this particular case, we can apply the central limit theorem, and consequently we can consider the standard normal. Okay, alright, 95% confidence interval, and I hope by now everybody got relatively comfortable with drawing the normal picture. It's kind of like this. The standard order is like this. Outline, center, which is the observed mean here, and end. There are two ends here, left hand side and right hand side endpoints. And shade. 95% inside, so the other 2.5% here and the other 2.5% there, that'll fall. Alright, and then we have the picture. Now, we can do the z-score computation, which is like this. End minus center over SE, the standard error. And please remember this formula number 1 of this course, the most important for the entire semester. Now, let's see, center 10.22, SE, sigma over square root of n, good. What's the endpoint? Well, this endpoint and that endpoint. This endpoint first, left hand side, okay, L minus center is 10.22 divided by SE. Sigma over square root of n. And that has to be approximately equal to the z-score associated to this point here. Left-hand side shading is 2.5%. So go to standard normal table. Shading is always to the left, so I want this one, so 2.5%. What's that z-score? Well, here we have the normal table, and look up 2.5%. Right here, 0.025, and that's associated to the score of negative 1.96. We have negative 1.9, and we have 6 column right here, negative 1.96. So this is equal to negative 1.96. And solving this equation, you're going to get the L value. And that's approximately equal to negative 1.96 times the standard error, 6.0 over square root of 100. And now, of course, if you flip this to the other side, then you get like this. And then if you punch in the calculator, you're going to get what you want. You're supposed to get something close to this. And from the center, we went left a little bit by margin of error z-score times SE. So we went a little bit to the left. Now, what if I want the right-hand side endpoint? I can re-establish everything, coming back here, and then shading to the left is 95% and 2.5%, so 97.5%. We can do all those, but it's going to be much easier if I use symmetry. I'm looking for now right-hand side endpoint, and by symmetry this becomes just plus, and that's it, just by symmetry. So from 10.22 center, I move to the right by the same margin of error, z times SE. That's how you can find the confidence interval. Let's do it again. Oh, by the way, there's full solution down here. See? Here and there. Now, 98% confidence interval. Similar problem, but different confidence level. Instead of 95% in the middle, I have 98% here now. So the other 2%, we have 1% here, 1% there. Okay, that's it. All right. How do you get it done? Z-score is n minus center over SE. This is very, very important. And left-hand side here, L minus center, 10.22, over standard error, which is sigma over square root of n. See? Sigma is 6.0 and 100 students. And that has to be equal to, at least approximately equal to, the z-score associated to this, 1% to the left. If you look at the z-table, shading is always to the left, so left, we have 1%. Look up the table. What is your z-score associated to 1%? The closest to 1%. Where is it? Right here. 0.0099 is the closest. This one is 0.0102, 0.0099. This is the closest. And this one corresponds to the z-score as negative 2.33. Negative 2.3 column and 3 columns, so negative 2.33. So negative 2.33. And then you can solve it. Like this. Just a routine algebra. And then if you want to find out the right-hand side endpoint, okay, no problem there. Just use a symmetry. This is now positive. Oh, R. So from the center, I move to the right by the margin of error, z times SE. Here from the center, I move to the left by the margin of error, z times SE. So once you set up the equation, you can easily solve it. From this equation, you can easily solve it. That's how you can get the endpoints of any confidence interval. If I change it into, say, 96% confidence interval, can you do it? 96% in the middle, and then 4% is shared. So 2%, the other 2%. Exactly the same problem, except that you'll have to look up 2% from here. And that's z-score. Okay, so much for confidence interval problems. Let's stop here for now.